Cool. Thank you, everybody. Yeah, it's great to be here. Been working at Modal for a couple of years, and this is kind of the first time that I've had an opportunity to talk externally about some of the stuff that we're working on. So I'm going to talk to you about fast, lazy container loading in modal.com. So if you don't know, Modal is like a serverless GPU cloud. We are serverless in the same way that AWS Lambda is serverless. Lambda obviously doesn't have GPUs, but we also have a very different application development and deployment model that's supposed to be fast and much more developer friendly. But it's particularly that serverless container loading thing, similar to what AWS Lambda is doing, that I'm going to focus on today. Cool. So I'll introduce the general container loading problem in the context of Modal. What we have here on the screen is a pretty standard Python ML prediction inference function. So we're taking in some text prompt, we're running it through a BERT language model, and we're spitting out a text response and some metadata. To give some context on the actual container that this Python process is running within, we're going to say that it's a fat container, it's about 8 gigabytes uncompressed. The runtime is going to be Python 3.11, which is a pretty common runtime to be running within Modal. And the model itself, the thing that is absolutely on the critical path to be able to run this inference request, is around 0.5 gigabyte. So we're running this container process. What does it mean to create the container file system? And you need the container file system for a container to start running. And basically always a container runtime is going to realize the container file system as an overlay mount on the host. And so without going too much into the details, an overlay FS mount is some kernel functionality that allows you to reconcile the mutations that happen against a read-only lower directory. So this is your container image in the lower, and this must be read-only, right? So you're going to start up your container image with this Python process. You're going to potentially make some mutations, but then if you were to stop this container and start it up again, you don't want those mutations to be still in your image. That's going to be very confusing. This breaks the deployment model. So the overlay FS is able to reconcile any mutations, have them happen in the upper. We throw away that upper. We keep the lower. You can reuse it. And yeah, this working directory, we can ignore it. Traditionally, the approach you would take to starting a container and preparing the container file system is the eager approach. This is the approach you're going to get if you're running basically vanilla Docker or Kubernetes. You can customize these things to not do this kind of approach, and many people are in response to the very same pressures that Modal is experiencing. But this is your typical approach. You'll probably find this on your laptop. The lazy approach is very different, and that's what's taken by Modal, but also by AWS Lambda. And so I'll explain at a high level how those two things are different. From the perspective of the eager approach, the container image that you would typically be Docker pulling or something like that is a fat stack of n tarballs, so one for each layer. And these tarballs are going to be gzipped for transport and storage efficiency. If you want to receive this container image on a cold host, so you can imagine a computer, an EC2 VM or a bare metal instance has come up and it's fresh, does not have this container image file system, you're going to need to download n tarballs over the network. If you're doing this properly, it's going to be reasonably fast. You're going to spin up some threads, you're going to pull from a registry that has a lot of upload capacity, you're yourself going to have on the host a lot of download capacity, you're going to be doing this at around 2 gigabytes a second. This is fine, this isn't really slow. But as I said before, it's basically always gzip stuff. And decompressing gzip is very slow. It's single-threaded, and you're going to hit around 80 megabytes a second. So this is slow. If we imagine back to the 8 gigabytes uncompressed thing that I said before, that might be something like what NVIDIA provides in their public registries, like a NVIDIA CUDA image. If we say a compression ratio of 2, you're going to spend around about a minute uncompressing this data. And then even if you've uncompressed it, you still need to lay that out on the host file system. So you're going to be writing a bunch of files against the host file system. You're going to be setting metadata, mode bits, all of this stuff. This is slow. You're looking at about a minute here to unpack fresh onto a host that's new, your data file system. And you must do that before you start up the container, because this is going to become the lower directory in that overlay FS mount. And if you're curious, I'm sure many of you have your own Kubernetes node. It is probably running the containerd runtime. You can look at this directory on a Kubernetes node, and you'll be able to see a bunch of regular file system directories that comprise the lowers of the various container images that you use. You might wonder why you would do this at all if it's so slow. This kind of like loading mechanism does fit like reasonably well with what a typical Kubernetes cluster is doing. It's running only a handful of applications. It's starting containers and stopping containers only relatively infrequently. And so you're going to need to load maybe only a handful of times. A serverless multi-tenant platform is not doing that. It needs to start containers very, very quickly. Maybe the set of nodes that is like running in this platform is changing very often. And so it's just a completely different cold starting profile to what your typical Kubernetes cluster has. Cool, so the lazy loading approach. It's very different. From the perspective of lazy loading, a container image is just an index. So it's just it's like the structure, a data structure, which has all the files and metadata about those files. And it's around 5 megabytes. And you can load this in 1 to 100 milliseconds, depending on whether you're just grabbing out of memory from disk or over the network. But it's a small amount of data. And so the index itself only has pointers to the actual file data, which must be present somewhere in your container loading system previously stored. And in modal, it's content addressed. It will typically be content addressed. So we've done a big change here of basically like not loading any data. We just loaded metadata. And so we've got a 1 to 100 millisecond image index load, and we're going to mount that using a fuse file system in about 2 milliseconds, and then we've got our lower directory. We can create the overlay FS mount. So we've turned something which would have taken about a minute into something that takes about 100 milliseconds. Best case takes like 5 milliseconds. So this is big for like being able to start the process. And we've kind of cheated though, you probably can see. But before I talk about the cheating, if you're not familiar with Fuse, Fuse is a file system in user space, and it basically allows you to create a flexible file server that can respond to the syscalls made by a guest process on a host, go through the kernel, and be served by your server that is free to do whatever it wants as long as it replies to that syscall appropriately. And so you can say, I showed you that Python program, it's going to want to open files in order to run. That open will go into the kernel. The kernel will then pass a Fuse message to the Fuse server. The Fuse server will handle that message. It will reply, we're going back into kernel space, and then that reply will go back into user space, this time reaching the guest process. You can see this jumping between user space and kernel space, and you're probably thinking, well, that's bad for performance. It is bad for performance. I won't go into too much about it. You could ask about me after. So yeah, I've pretty much shown you like not a free lunch. Like there's no file data loading going on here. How do we load the file data? This is where our problems begin. If you need to load the file data, you're going to load it from one of these 5 cache tiers. So our Fuse server is going to receive a read request, and if things are going well, you're going to serve it from memory. Your latency on serving and accessing that data is around 100 nanoseconds, maybe less. You've got reasonably high read throughput, and the cost is quite high. Cost I won't talk too much about, but this is like obviously a factor in building like cloud economic systems, is the cost of these various caching tiers. If you don't find it in memory, which is probably going to be the page cache of your host, you're going to drop down to the SSD. Does the host have this file on its disk? In a very fresh host scenario, in a cold start, it's not going to be on disk. Like this system has just started. It's a fresh disk. So then you're going to have to drop down to over the network. And you've got an AZ cache server tier. So this is something that's co-located in the availability zone that you might find in AWS. It's going to be about a millisecond away from you. And you're going to have reasonably high read throughput. Because at this point, you've like not hit a local cache tier. You're in a kind of a bad way, but not such a bad way, because you're only a millisecond away and you can do a lot of data reading very quickly. If things get worse from there, though, you're going to drop back to a regional CDN tier. And so this thing, we're really blowing up the read latency. We're at 100 milliseconds now, not 100 nanoseconds. This is bad. We do still have quite a fair bit of read throughput, but this is a huge span of latency, and we could have our guest make a read request against the file system that could be served from any of these tiers. The only guarantee is that you have the data in this tier. This is like our origin store. If you have a pointer in an index, that index pointer will always resolve against this tier. But it's 200 milliseconds away. So if we were to serve reads sequentially, 200 milliseconds every time, you're going to wait like hours for like a Python process to start up. So if any of you are sensitive to like very fast movements, close your eyes. But like I did want to give you a very visceral sense of like what it looks like for these like latency tiers. It should start. Cool, so at the top we've got main memory, the bottom we've got CDN. The CDN's like what tectonic shift, it's barely moving. And like I like to look at this stuff because like you really see like, there's 100 nanoseconds, there's 100 milliseconds, what is it like? It's like the difference between good performance and like an absolute disaster. How do I get this thing to skip now? Cool. But unfortunately for Modal, or at least like it's just the reality, it's just a fact of our business, that we do have those entire tiers to deal with. We have a global worker pool, we are in the spot markets, and so we're subject to preemption, and we have instances running all over the place. We have a lot of instances running in US East 1, which is where our origin tier is, but we do have instances running in Japan, in the Middle East, and occasionally we've run in my hometown of Melbourne, because there were some H100s there. And H100 is pretty hard to get, but there was like 128 hosts over here, so we're like, sure, we'll run them there. Things may look bad now, like you've seen how slow that dot was, but there is like reason to be encouraged. Like this is solvable. Like we've had multi-decade trends where the bandwidth of our computing systems have been improving faster than the latency of those systems. And so we're getting more and more experienced in building and optimizing for the capacities we do have and not for the very small amount of latency that we don't. The other thing is, in recognition of the latency lags bandwidth reality, we have to cache. And caching does work pretty well. Modal is it's a pretty general container runtime, but our customer base is like Python, AI, ML stuff. And there's a lot of overlap if you do this like lazy loading system that we're doing. You're basically loading Python 3.11 libpython once, and then a bunch of containers are using that as they start. So like the first time you run that, you're accessing the file, you're storing a disk, you might store it in your page cache, then you're golden. And this diagram here is just showing the overlap between PyTorch, a Dreambooth container image, and then some other random like Hugging Face one. There's 8.7 thousand files in common. And so this is great. The overlap is great. Also, another thing that I won't like talk a little bit about is, but it's worth mentioning, most of the stuff in a typical container image, especially a fat one that's like 8 gigabytes like the press.disk, is junk that will never be read by your process. It is absolutely useless to load it, but an eager loading system will load it because it's like getting those tarballs, they have like /etcd/locale, your process is never going to read locale data, you're loading it anyway. It's a total waste of time. Cool. How am I going for time? Good. All right, let's get into the system architecture. This is a simplified system architecture of how we do lazy container loading in Modal, and it should look pretty similar to that table of latency tiers. So we have our container process in the top left, Python main container. That's accessing a Fuse file server, and that Fuse file server is going to access the page cache, if not the SSD, if not jump over to the CDN, if not hit the blob storage. Really bad, this should not happen often. If it's happening often, we'd have done our job properly. Okay, given the overview of what we've built and like how it works, let's talk about like how we actually improved performance, how we got on the grind, because we used to be in a place where taking that single 512 megabyte file, that BERT model file, we would load it at like a peak throughput of around 800 megabytes a second. So you're taking the better part of a second to load that absolutely crucial file, and models have gotten bigger than this. So you're thinking like your LLM models these days are in the tens of gigabytes. If your peak throughput is 800 megabytes, you're not in a good way. We have improved it quite a bit. We wish it was higher, but we have improved it quite a bit. It's now about 2.5 gigabytes, and I'll tell you some of the things we did to get to that throughput range for a Fuse file server. And yeah, just a quick recap, like I'm gonna focus of the Fuse file server's performance on its like read throughput on a single file. Obviously that's just a slice of the performance situation you're dealing with, but we have a short amount of time in this talk. Let's start simple. Don't use small hosts. If you use a small host, the cloud providers, we run on the cloud providers in the spot markets, are not going to give you enough bandwidth in your SSD and bandwidth in the network to be able to drive peak performance. And obviously, when a container lands cold on a cold host, you are governed by peak performance. You really want your network performance to be much higher than your Fuse performance. You do not want to be bottlenecked on your network, so aim for around 4 gigabytes at least down. Make sure you're not limited by the cloud providers' limitations on single flows. And they also can throttle you for weird reasons, and you have to contact them and make sure that you're getting the peak throughput that they advertise in their documentation. So the single flow thing is, they may advertise that your instance has 20 gigabit down, but they'll say only 5 gigabit for a single flow. So you've got source IP, port, destination IP, port, protocol. That 5 tuple is a single flow. You need multiple of them to actually saturate your network throughput. So we had to worry about that at some point. We're like, why is it so slow? Like, we have like a lot of network capacity here. You don't want to be going over a single flow. You want to stack a bunch of SSDs together. We're doing RAID 0. These SSD tiers are not the place we need to be durable. Like, the origin tier is where we don't lose data. So get your throughput, stack a bunch of SSDs together at RAID 0. And just to give a specific example at the bottom, this AWS instance we do use quite a bit. It has A10G instances, A10G GPU devices, sorry. And yeah, it gives you around 5 gigabit a second down, or gigabyte a second down, and has a large SSD. This is where it gets harder and probably more interesting, is all of the Fuse stuff. You've gotten a big host at this point. It has like high peak network bandwidth and like SSD I/O. You're going to get into the nitty gritty now. So as I said before, we started at around 800 megabytes a second peak read. This is not good enough. We were lagging far behind the capability of the NVMe SSD and the network. Yeah, I've already said the thing about what we're focusing on. So this is probably the biggest bang for your buck. We increased read ahead a lot. So read ahead is something in the kernel that allows the kernel to request future pages when it receives a request for a particular page. The default in the Linux system, for quite sensible reasons, is 128 kilobyte, which is a handful of pages, 4 kilobyte pages. Doesn't work at all if you have really high latency, because you could be falling back to the network. So we've set ours at 32 megabytes. This works for us. Can you just increase it forever? Absolutely not. We were feeling good that we found this performance improvement because we tried it locally and we're like, sweet, this improves capacity. Let's ship it. We shipped it with like accidentally like 1 gigabyte and then blew up latency in production. So if you tell the kernel to read a gigabyte of data, whenever it gets a single read request, it will do that, and things will not go well. Another thing you can think about is Fuse request size. So that trip from the guest process, you're going to issue a read sys call. It's going to enter into the kernel. The kernel is going to materialize a Fuse request, and these are sized. And so ours was sitting at 128 kilobytes, same number again, and we got it to go to 1 megabyte. As we want peak throughput, we want fewer, larger requests, more efficient. We couldn't get this to go higher without enabling direct I/O. We haven't been able to figure it out. Maybe someone has, but we would like this maybe to be higher. Maybe we'd like to try going higher, but we've been stuck at here because we do not want to disable the page cache, and that's what you get if you do direct I/O. So any write with direct I/O is going to bypass the page cache. Any read is going to bypass the page cache. We like the page cache. It works really well to coalesce reads, serving them out of memory. It's a good idea. And then another knob that you want to tune is your congestion and max background. So the Fuse system in the kernel is going to fulfill the requests either on a synchronous path or a background. And it does this because some things need to be served quickly, some things need to be buffered. Pretty normal. Read requests are buffered. And so if you have a Fuse server that you want to be configured for a different read-write pattern, you may not increase these things, but because we are a read-only file system, because we are so read-heavy, we want to blow up these like queues in the background system as large as possible so that we're not throttling the guest because they've backed up on their reads, and then only synchronous requests will get through. To give you an example of what a synchronous request would be, like requesting file metadata might be, or a lookout. Finally, after you've twiddled all your knobs, you still need to write good software, unfortunately. And you don't want to blow up your heap. So we were finding, I didn't actually do this, my colleague did, but he profiled this. This is a flame graph. Unfortunately, there's like not enough pixels here to see what's actually going on, but there's a lot of allocation going here. There's page faulting at the top. We're spending 50% of our samples on memory allocation. We're like, this is bad. Having a large heap was really dropping our throughput, and reducing the heap size while we were pulling through these large files was improving our throughput. And why we were blowing up the heap is because when you issue a read and it goes over to the network, we want to get that into the disk and the page cache so that any subsequent reads against that data are served not out of the network, but out of the page cache and out of the disk. But in order to write to the disk, we were holding all that file data in memory and blowing up our heap. And so the thing we did at a basic level was just defer any disk writing, keep your heap small, stream the data from the network to the guest process without holding it in memory. This was worth about 100, 200 megabytes of increased throughput. And yeah, that's all I've got for you. So summary, get big instances, that's simple. With these changes and some others that I haven't been able to talk about, you'll get up to about 2.5 gigabytes a second. If you've got significantly higher than that, love to hear about it. And we can load this like 512 megabyte safe tensors file in around 200 milliseconds from disk cache and 300 milliseconds from the network, which is a lot better than the better part of 1 second. But this is not enough, and that's a story for another day, basically. I think that's all I've got. Yeah, of course, thanks to Phil, Angelo, everyone for organizing, and obviously big thanks to Eric, Akshat, Eric again, Luis, Dano, and Stefan. They really brought this system to life. I'm just up here talking about it. Any questions, I guess?
When you get the question, can you repeat it?
Yes, I will repeat it, yeah.
So you mentioned at the end, well, first of all, great job. I enjoyed the talk.
Thank you.
You mentioned at the end that you're just going straight from the network to the user request for the read.
Yep.
So I'm wondering when or how do you actually do the caching on the...
Yeah, it's a good question. So the question was like, I talked about how we defer disk writing. We don't want to like blow up the heap. We also don't want to bottleneck on the I/O performance for writing of the SSD. So we're able to keep like a reference to that data chunk, and then we will just fetch it later. So we build up a queue not of the actual byte data, but we will say like this particular pointer and this like block. That's another thing I didn't get to talk about, but like the actual origin store is like chunked. Everything's not stored like in a single blob. So we're doing like, you know, a certain chunk size, it's 8 megabytes, and so we'll say like these offsets, this file pointer, build a queue of that and burn that down.
Cool, thanks.
Yep.
You mentioned at the beginning that to make the fuse call, you trap into the kernel, and the kernel calls, and
Yep.
you trap back. Can you avoid that? Can you avoid the...
Yeah, it's a great question. So the question was about when I showed the fuse system at a high level, you're jumping between user space into the kernel, into user space, back, back. This is bad, you're context switching, you're introducing a bunch of overhead, you're lowering your performance. You can actually, and this is more knob tuning so far we've done, you can like set certain settings which are appropriate to your read-write pattern. So if, for example, you're read-only, you can set certain settings in the fuse system to say, don't tell me about open requests or open directory requests. I'm not going to do anything special in the server when you give me this, so it's absolutely useless to tell me about it. And then the kernel will receive it and it'll throw it away, or it'll reply with whatever appropriate reply the guest process requires. We want to do this because, yeah, it does drop the latency of these certain operations. Yep.
Do you have to think about either corruption from these read requests or misdirected reads, where like you've requested something from somewhere and it gave you the wrong thing?
Right. We do have to deal with corruption. We've had to we do a lot of checking on the write path that we are writing the correct data, and we will also check lengths on the read path. We won't like hash and compute digests of like the data that we're getting. That hasn't been a problem. But yeah, we have had the problems in the past where we've had a write corruption on some disk-cached block, and then we've detected that so far with like, is this the right length? And that's really like solved the problem for us. But yeah, we definitely did have these corruption issues. Yep, the one in, yep.
Have you done any experiments with like pre-provisioning like common base image data on the hosts before they move?
Yeah, that is a great question. There are so many things that we should do, and that is one of them, yeah. We would want to build like some sort of prioritized list of like most common blobs, like because the system is agnostic of whatever it is, just give me these blobs, and then every host that starts up should have at least these blobs. We will want to do that, yes. But we haven't yet. Yep, blue shirt.
Did you ever do anything with trying to make slimmer containers as like a first step, or did that?
Yeah, that's a great question. Everything is not like so bad as having like an 8 gigabyte uncompressed like fat image. Modal is like going to let you do that sort of thing, but we provide slimmer, like we use Debian Slim as our base image, and with the way that GPU packages or ML packages are like packaged up these days, they usually don't need to have on the actual like container a bunch of these like heavy libraries. They'll bundle it into the wheel, and so you can have a relatively slim image. We say to our customers though, like this doesn't matter. Like we're going to build a system that if you have like 1 million files and then like you only need like 1,000 of them, we're going to build the system that just loads those 1,000 files, and it doesn't matter about the actual size of the image. I mostly use that 8 GB uncompressed to give a contrast to what an eager system is going to do, and that's where that's going to really suffer. And that's what I experienced in my previous job, actually, was like we would build like fat containers with all this sort of stuff. Like you could run TensorFlow, you could run PyTorch, you could run whatever library you want, and the actual image was like huge. Yep, maybe in the front, yeah.
Did you ever run into any issues where like the latency did become a bottleneck? Are there like certain patterns with the containers that could make that happen, or is there something about the way people structure those that prevents it from being an issue?
Yeah, like the latency is definitely still a bottleneck. It's a constant fight. Yeah, being a serverless cloud provider, cold start performance is the most important performance, and it's like never really good enough. Like AWS Lambda's system, I linked their paper, like on-demand container loading in AWS Lambda. A lot of the similar things you can read, it's a great read. You really need to fight to get down into the sort of performance like area that they're in, which is like sometimes like 10 milliseconds, 20 milliseconds to start up. We are definitely not where we want to be with latency. So we're doing these things of like trying to avoid trips into user space from the kernel. We're even thinking about using things like EroFS, which is something you load into the kernel and it avoids like a trip outside into user space entirely. We're thinking like, why is like every individual operation from guest to Fuse server like having such latency? We also run a user space kernel called gvisor shipped by Google. So we have an additional tier of like slowness where there's a syscall being intercepted. Yeah, so there's lots going on and the latency is not where it needs to be, but it's pretty good and you can try it out on Modal yourself. Keep going, yeah? Sure. I think the back with it, yeah.
Yeah, kind of related to the last question, and I realize this is a large topic, but often what you see with like the Python interpreter is it loads a bunch of files serially.
Yeah.
So you get one after the next, this file, then this file, and you don't see the next request until that first request is completed. I'm wondering, do you have any tricks for dealing with that, or is that just one of the bottlenecks?
Yeah, that is a great question. So the question was about like the serial nature of a Python process is it doesn't like make concurrent requests for like, I need these 1,000 files, give them to me as quickly as possible. It'll say, I want to load this particular module, and then that module will be loaded into memory, execute, and say, actually, this one depends on that one, and you're just going to follow this like linear walk. Yeah, and if you don't like know about that ahead of time, and your latency on the individual operation is too high, you're going to also slow down. This is mitigated significantly by the AZ caching tier, which we used to be much more invested in. When you're only a millisecond away, perhaps less, if that's being served out of like the memory of the AZ cache. The occasional hit on that is going to be fine. We used to have that as sort of like the thing we were betting on. We now have divested from the AZ cache, and we're much heavier on the regional and the origin store. And so having lost that tier, we do a thing called task profiling, where we like see what the process has done, and then we record that, and then we aggressively preload before the container even starts up. And we need to do that. Like you can't get away with it otherwise with the 100 milliseconds away from your like file data. And then you may ask like, what happens if you've like never seen that container before? You just do pretty simple heuristic stuff. Like, what is a Python process going to want? What's a machine learning Python process going to want? And that generalizes across runtimes as well, right?
Good.
Yeah. One more, yeah.
So I'll caveat this by I have no idea how this interacts with the Fuse file system stuff, but could you use something like IOU ring at all to like improve the performance jumping from your like user space through the kernel, etc. at all, like of those system calls?
Yeah, like I have to say that I'm not very experienced at all in IOU ring, but like the idea of doing, I think, like this asynchronous like model, and like you can drive like higher performance out of your disk. Yeah, we haven't really explored it much. It's very much like in the sort of backlog of things that like maybe, yeah. Cool. Well, thank you everyone for listening.